So I'm going to explain to you a little bit the core details of the Truffle system, which is which we call the Truffle API. And after that, I'm going to explain a little bit how we do speculation in Truffle, really just using code examples, no theory. And the third part, I will do some quick demos until I give the mic again to Thomas. So in Truffle, everything is a node. So you usually start off with declaring your node. You give your node some execute signature. Like here, we have an execute that just adds up 2 integers and returns the integer. The node needs to return the node superclass. And the node itself has some facilities to replace and so on. And to make this optimizable for Truffle, you need to wrap this node into a so-called root node. This is also guest language defined. And the guest language, the root node might have some, sorry, you can't see this, some child nodes, and might have multiple child nodes, might have an array of child nodes. And then the root node, the difference between the normal node and the root node is that the root node has a defined execute signature so that our framework knows what to call. And you can also see that the root node gets a virtual frame here. That's what Thomas was talking about. That's basically our representation of the stack frame. And all accesses to it get virtualized, so they're allocated on the stack in the end. And of course, all the virtual calls you do get eliminated by partial evaluation. In order to optimize this, you need to take your root node. Sorry. Pointer works. Allocate it. Wrap it into a call target using Truffle get runtime create call target. And then you get your target and you can call it. And if you call it multiple times or often enough, the framework might decide to optimize this and compile it in the background to machine code, as we've seen. So let's talk a little bit more about this Truffle runtime interface. It provides several facilities to implement your language. We already talked about the create call target thing. That takes a root node, wraps it into a call target that we on the runtime side implement, which does all the logic to make it run fast. And we have several other utilities in the Truffle runtime. I don't want to iterate over all of them, but I want to show some of them. So one important aspect is that if you want to call into other call targets, you can either use a direct call node or an indirect call node. These are also predefined nodes that we define in order to support things like guest language stack traces. The important thing to note here is if you create a direct call node, the Truffle system is able to do inlining and also EST duplication for polymorphic call targets. And if you have a megamorphic call site and you don't know what to call, you create an indirect call node that you can call with an arbitrary call target. And of course, as I said, you can also iterate over frames using a frame instance visitor, and there are several others that you can look up in the API. I think there's a link in the description of the SimpleLanguage project. Another important part of the API, of the Truffle API, is compiler directives. These are functions that are intrinsified by the compiler, so the compiler knows something special about them. So one of the most important ones is the transfer to interpreter intrinsic. So you can call this in any place of your Truffle application in your node, and it will transfer the state from the compile code to the interpreter again. And there is a separate thing called transfer to interpreter and invalidate. Additionally to transferring the state from the compile code to the interpreter, it will also invalidate the underlying compile code. There is a second. There are also several annotations that you can use in your Truffle interpreter. For instance, there is compilation final. You can have a multiple local field in your node class. You annotate it with compilation final, and the compiler will think it will be stable. It will not change anymore, and will see it as a constant. Another important interface is the value type interface. You can add it to immutable types. And so the compiler will just ignore identity semantics for this object and can do further optimizations with it. And another important one is the Truffle boundary thing. Sometimes you just want to call into Java code. Truffle partial evaluation escapes expands really every path you go through your program. So the graph might become really big. And if you want to just call into a Java function that does something on the slow path, you can annotate it with truffle boundary, and the partial evaluation will stop at this point. So I'm going to use in the next examples that I want to present just these three APIs, basically. I want to have a node. I want to transfer to interpret and validate, which is transferring the state from the compile code to the interpreter, invalidate the local compile code that is behind it. And we have used compilation final to make field accessors constant for the compiler. So let's assume we want to implement a negate node. It's a very simple negate node, which takes an integer as an operand and just negates the value. Let's assume now that our language is really weird. Like dynamic languages have sometimes really weird semantics because they don't really have a specification, and sometimes they have just weird behavior. Let's assume that our negate node has this behavior. If the value is integer min value, it's not actually integer min value if you negate it, but it's integer max value. So you would implement a corner case like this. We would say, OK, operand equals integer min value. And if it's integer min value, we will actually return integer max value. And else, we return just the negation. Yes, please.
Why is the operand and int not some sort of node?
Why should it be a node? So the question was, why is the output not a node? Because these are the values that flow through the interpreter. These are usual normal runtime values. And the AST itself is declining using child fields that I've shown with, and they are not actually flowing through the AST. You can wrap them again into a root node and then into a call target and then flow it through the AST, but just nodes don't flow through the AST usually.
And what if your language doesn't work on ints, but on...
You can just use arbitrary types here. This is just an example.
Okay, so then you would use big int or something.
Exactly. But I will come to this, how we separate types and how you define multiple specializations later on. So we want to now, since this is a really corner case and our operand is very rarely integer min value, we want to speculate on this particular value to be not integer value. So we say, OK, we create a compilation final field, which is a Boolean, and we call it min value visited. We annotate it with compilation final. We check if min value visited is false. We de-optimize, set it to true. And yes, so what the compiler will see in this case, the compiler will assume that min value visited is constant. So if the compiler, when this method is compiled and it sees a true, it will just compile the full method. It will just say, OK, operand equals integer min value, return integer max value, and then do the normal negation. But if the compiler sees min value visited false, there is now an important difference. Now the compiler sees an operand equals integer min value, transfer to interpreter and validate, and return just the minus operand. Why are these two versions different? This one introduces a merge in the control flow that we have seen, and this one does not. This will just de-optimize. So the compiler has a lot easier time to just see this value, so it can do a lot more speculations on this result value. So we don't have control flow anymore. Yes, please.
Can you tell again what does compilation final do?
Compilation final is compilation final annotates a field, and if this field is read, so the compiler sees a read here, it will assume the value will not change anymore. The important thing is that if you change this value, you need to de-optimize, of course, otherwise the compiler will not see it.
So somehow it's some sort of binding time analysis, like manual binding time analysis. So you're making it a statically known value.
Yes. Yeah. And if this value changes, you need to de-optimize always. If you would remove the transfer to interpreter and validate, it will actually never see this field right, because it will always assume it's false.
The whole kind of binding time analysis for partial validation.
Sorry, I don't get your question.
Okay.
Yes.
There are more questions?
Oh, yeah, please.
Sorry, I think I missed something important here.
Yes.
So
I understand why you want the code on the bottom.
Yes.
And the code on the bottom could end up generating the code on the top. Is that the idea?
So if this case is actually triggered, we de-optimize, and we would go into the interpreter back again. We will set min value visited true.
Mm-hmm.
And the next time it gets compiled, it will see this version. So it will invalidate the whole compilation unit. Did this answer your question?
So in this case, it seems like transfer to interpreter and invalidate's not a great idea because the code would be just as small if you did it directly. But I could imagine in other cases it's going to save you a lot of space until you need it. Is that the point?
Yes, but the code is the same size, but the point is in the code below, the compiler will not see a merge point of two control flow paths. And so the compiler will be able to optimize this code below a lot better than the code above.
The one on the top generates a merge and the one on the bottom does not.
Yeah, because transfer to interpreter in the compiled code is kind of like, get me out of here, right?
I see. Okay, now I understand. That's very, very helpful.
Yes, please.
You mentioned compilation unit for transfer of interpreter. What's the compilation unit here?
So
how much do you recompile and where do you to stop?
So the compilation unit is always the call target. So from the root node, every child node does it sees. And if you have direct call nodes, you might also inline through other call targets. So the compilation unit might be big, and always the full compilation unit is invalidated.
So in theory, you could have kind of nearish the root node, you have a transfer interpret, and then if something changes, you recompile the whole program again. Or
not the whole program. So not the whole program is recompiled if you transfer to interpreter, but just the call target. So one particular function or function and the inline functions.
okay, function.
So if I say compilation unit, I mean a function that is compiled usually in a language with all the inlinings and stuff. Yes. Yes, please.
Couldn't you statically see that you reassign a field that is a compilation file node and automatically insert the transfer to interpreter and invalidate this call?
Yes, it would, but it would not be Java anymore. Yeah, but it's possible, yes. Would make life easier a bit, yeah. At least what we want to do is we want to statically check that you don't make mistakes. Like if you see a write to min value visited and there is no transfer to interpreter, we want to verify this. We're currently working on this. So since this is a pattern that we use a lot in our interpreters and we want to speculate on unlikely branches, we introduce so-called profiles, which basically is the same thing, but it just encapsulates. So again, don't be scared about abstractions. We just create a branch profile instead, which is the min value profile, and we create branch profile.create, and in this case, we just call min value profile.enter, which does the exact same thing, but saves you a few lines of code. And we in our interpreters, we don't just want to speculate on branches, but we also want to speculate on conditions, full conditions. So we also have condition profiles. Here we create a small binary condition profile. We can use this profile on the condition here, operand equals 0, smaller 0, return minus operand, and return the normal operand if it's not true. The difference between a branch profile and a condition profile is now that the condition profile speculates on both branches. So the condition profile has 4 states. So either none of the branches were visited, so it will immediately de-optimize in any case. The code was not executed. Just the first one was visited, or just the second one was visited, or both were visited. So ideally, if the value was always negative or always positive, we again save a merge. Yes, please.
This sounds like strictly superior to the previous solution. Is that the case?
Not necessarily, because you don't want to always speculate on both branches. So if you have really an unlikely branch, you just want to cut it off. Yeah. But good question. Yes?
So if you put it in a while, is it doing somehow a similar thing to loop peeling?
No. So if it is similar to loop peeling, if you put it in a while, no. More questions? Okay. So sometimes you also want to speculate on a little bit more complex things. For instance, you want to speculate on the fact that the incoming value is actually a constant. You can do this by using the identity value profile. The identity value profile now has 3 states. So it starts off in the uninitialized state, and it will basically, if it starts off in the uninitialized state, it will just fold this value, and it will directly go into the else branch here. We transfer to interpreter and validate, and if the cached value is uninitialized, we will initialize the cached value with the incoming value. And the second time we execute the identity value profile, we will go into this branch here, and we will check if the value is still the same. We are not returning the incoming value, but we are returning the cached value instead. So the compiler will assume that, again, this is assumed constant by the compiler, so it will see that this identity value is constant. This comes at a cost, because you need to introduce this check. So this is a dynamic check from a constant value to the incoming value, but sometimes it saves you a lot. Of course, if this is not the true anymore, we will transfer to interpreter and validate again, replace the cached value with our generic field here, and we will, next time, if this profile is compiled, the whole profile will just fold to an OOP. You can also do this using types. So if you want to inject types for your compiler, you will just do the same thing, but now we have 3 states again. Now the uninitialized state is represented as null. In the null case, we will just get the class, initialize our branch compilation final field with value get class, and if the in the normal check, we check if is this cached run is instance of the incoming value, and then we can use cache class.cast. Important to see here is that the compiler sees that since this cache class is constant, can turn this into a normal instance of check. And also this cast becomes a simple cast. So this way you can tell the compiler, please try to cast this incoming value to an explicit type. So let me quickly summarize of these kinds of profiles that I've shown here. So there are the branch profiles to speculate on unlikely branches, condition profiles to speculate on binary conditions where it's not known which branch is unlikely or not. Then there are identity profiles to speculate on constant values, and type profiles to speculate on constant types. So what are the limitations from this? So, yes, please.
Good question. So if you don't use any of these profiles, the compiler will not do any profiling.
There is, yeah, not much, yes. So you have the full control over the profiling. That's important. So you tune your interpreter basically by putting in these hints for the compiler, so the compiler can do a better job. You usually don't do these optimizations yourself. You just tell the compiler, hey, try to optimize this by injecting an aesthetic type, and the compiler will do its best job that it can do. So what are the limitations of this profile? Yes?
So if I understand correctly, if you have a program with an unlikely branch, it will ignore it first, and as soon as it sees it, it will recompile to take into account. But what if and then thereafter it will be slower for every implication?
Yes, yes.
Wouldn't it be possible to, if this branch happens once every 1,000 calls, to just take a slower path, but not recompile everything, right? Much like exceptions, which are considered exceptional.
Yes, yes. You can. So the question was, if an unlikely branch just happens once, will it pollute all the subsequent compilations? And yes, we have heuristics in place that try to mitigate this. So the will split call targets to re-initialize the EST, and so if your EST is polluted, and also if your phase shifts in your application, our heuristics try to find out when this happens and will re-initialize your EST automatically based on heuristics.
Yes, and also you could modify, if you can go back to this, maybe to the branch profile or something. Yeah, you can modify your code here to say in this else branch be not immediately transferred to interpreter and invalidate, but we have some check that you would only do when we enter there, and then if the check tells us this is a rare case, we just do transfer to interpreter and not invalidate.
Yes. So what are the limitations of this? Of course, identity profiling, type profiling just works for a single type. So there is this famous technique called inline caching, also introduced in the 90s. So you can chain multiple versions of the same node, same types together and duplicate the code behind it. And the other limitation is that it's for local speculation only. So it just invalidates the current compilation unit, and it will not react to changes outside of the current compilation unit. So for that, you need non-local assumptions. And I will talk a little bit about these non-local assumptions. Non-local assumptions are like Booleans that start with the state true. They are valid, and they are just invalidated once in the application. But these assumptions are known to the Truffle system, and as soon as this assumption is used when the interpreter is compiled to native code, it will register the native code to the assumption, and as soon as the assumption invalidates, all the registered install code versions will get invalidated. And you can create these assumptions by calling it to the Truffle runtime like this. So how can this be used, for example? So assume you have some instrumentation for your language, and you can look up some assumption and you store it in a final field. Since this is a final field, Truffle will assume that this value is constant also. And then you can just check if the assumption is still valid. You don't need to do anything for instrumentation. If it's not valid anymore, we need to instrument. So at some point in the application, the instrumentation system will just invalidate the instrumentation disabled assumption, and all the code that were relying on it will get invalidated and recompiled using the now added instrumentation. The important thing here is that this check actually compiles down to no op. So there's no overhead for this exact compile time again for this check. Yes, please?
Regarding that final, did I understand correctly that basically because the reference is final, the framework assumes that the value is also final? Because that's not usual Java.
Exactly. The question was if the reference to a node is final, it also assumes that the assumption is final. Yes, that's the case. That's one of the assumptions we take during the partial evaluation. So what are common use cases for non-local assumptions? For instance, if you want to speculate on function redefinition, so you want to cache your method lookup in your language. You want to check, oh, this is still the same type and still the same symbol. I can just return it and don't really need to repeat the method lookup. But in order to ensure that this is still valid, we need to verify assumptions that in the meantime, the function that I've looked up was not redefined. So, so if the case happens that the function is redefined from another part of the application, the code gets invalidated and will redo the function lookup again. You can use it for assumed global values. So if you have config parameters that just rarely change, like instrumentation or something like this, you can have a zero cost check without to enable these kind of things like tracing, debugging, instrumentation. So the other problem I was talking about was that the profiles were lacking the ability to get polymorphic, and to implement to get some polymorphic behavior and also polymorphic speculation done, you need to implement inline caches. And an inline cache basically works like this. You start in the uninitialized state, and then so the value is not instance of anything, and you have no value guard, so it will be immediately a de-optimized. So we get now our first value in, so for example an integer. We will now rewrite our node and insert a node that does an instance of integer check, and then we do our integer case. And if it is not the case anymore, we will just go into the fast branch and de-optimize again. And in this de-optimize, we will also rewrite the whole inline cache again. So for example, if we get now a string value into our inline cache, it will now just chain these versions together. So it will check for the instance of integer, do the integer part, instance of string, do the string part. The important thing to note here is that this needs to be final, so we cannot just go and replace this inline cache with a string version, because this will trigger de-optimization in a loop. So we want to reach stable state for the AST at some point, eventually. Since this is sometimes can be quite difficult to implement, we built on top of Truffle, of the Truffle API, we built another DSL that is based on Java annotation processes to generate all the boilerplate, to do the rewriting, to ensure that the inline cache is actually thread safe and that there are no duplicates injected and so on. So there is some important parts that need to be done if you do this manually. So we define this DSL, and this DSL basically, instead of defining one single execute method, you define multiple methods that are annotated with specialization and that represent each individual case of this operation. So we can just say specialization to the integer version, and then in case we get an integer value, we do our int implementation. In case we get a double value, we do the double implementation, and for string, we do the string implementation. The important thing now is it will exactly do this semantically, so it will try to chain the instance of integer, these cases together, and it will just chain these cases together that were actually triggered in the interpreter. That's the important thing. So it will do the inline caching for you automatically. Yeah. Yes.
A very common case is that you've got some operation that works on all these types, and it's called from different places in the code. And over here, it's always called on integers, and over here, it's always called on doubles. I presume in that case, you don't build this chain, but you would just have 2 copies of the code.
Yes, we have 2 copies of the code in case this is polluted, yes. But this is again based on a heuristic, so this is not perfect. It's just on a heuristic based. Also because there's the trade-off of code size, and you need to have an upper bound on how many of these call targets that you duplicate. Yes?
So here in your DSL, the order of methods also matters, yeah?
Yes, the order matters in which you define the methods, yes. So it will be tried in this order, which is actually not Java semantics, because Java semantics does not use the order of the methods. But you can get this in the annotation process API, luckily. So what we can do now is we can take the concept of an identity value profile and expand it to a polymorphic identity value profile by just defining a specialization that caches now on the operand value, stores it in a field, and the DSL will know this cached annotation and will try to store it in a field of the actual specialization node. And then we check if the operand equals still the cached operand, we can do our implementation for a particular value, a constant value. So this value we get in, the compiler will see that this will be always constant. And since we can get arbitrary different objects, we also need to define a limit for our specialization. How many instances of this single specialization are going to be created until it bails out? So in case this limit is reached, so we found 3 different identities for our operand, we will just go to the next specialization that is defined, and we will ignore this one from now on. And in case, so we now have a different implementation that does not check for operand equals cached operand, just like the generic case in the profile, and you can define your implementation here that does on identity without constant value. What we also define here is this contains attribute. And this contains attribute actually specifies that all the instances of this specialization get removed from the inline cache if this case is triggered. But this is optional. So if you don't define the contains attribute, all the inline cache entries will remain, and we will just add a generic version in the end of the cache. You can expand this concept also for types. Works similar like the type profile. You can have multiple types and multiple types that are casted. So instead of caching the operand, we now cache an operand.get class. And so this is considered to be constant. And then we use the cache class.cast operand, and we can use a constant type in this implementation. And again, we need to guard on this. So we need to insert a check to ensure that this is still the case. So let me quickly summarize this. So use profiles where monomorphic speculation is sufficient. Sometimes it is. It also makes the code sometimes a little bit more readable if you don't need to split up your code in multiple specializations. You can use inline caches for speculations where polymorphism is required. So if you want to handle these cases, so you want to tell the compiler multiple different types for this code because it's very complex and it gets reduced a lot if it knows the type, for instance, you can duplicate the code and tell the compiler. And assumptions for global speculation. Any questions so far? Okay, then next up is my demo, the fun part. We will use again the simple language as demonstration language, which is our demonstration language for Truffle features, and it's actually very well documented. So if you look at it, there should be a lot of Javadoc in there, a lot of inline comments to explain every single thing we do. So if you get through it, it's a good read. And I will start with my division speculation example. So yes, I used the same example that Thomas used before in his examples, but I added an additional division here. And this division, the divisor actually comes from the outside world. And since we are just compiling this particular method, it cannot see that we actually are passing a 1 to the value. But I also want to emphasize the point that this value just might not be a constant value, but might come from a stream or some outside world that we don't know of. So this is completely a dynamic value usually. But in this case, we just pass it here, for example, but the compiler does not see because it just compiles tests. Our harness is written in a way that just test is compiled. So what happens now if we run this? Is that the compiler cannot see that the division is actually 1. So it will always insert a generic idiff instruction. And as in the previous chance, we were down to 0 milliseconds somewhere, and now we are up to 10 milliseconds. If we run this...
Can you go to one of the other windows? Like,
yes.
Yes, that's next one, otherwise
okay.
That's good.
Yes.
Simple language, sorry. Yes, that's good.
Yes. Can you read it now? Okay. So now let's look. Yes.
So this simple language,
yes.
You have somewhere an interpreter for the simple language?
Yes.
And that's the basis for what you're doing?
For the compilation, yes. We will modify it later.
Before you show us how to make it fast, could you just show us how to make it and give us a quick tour of the description of the simple language?
So the simple language, unfortunately, it's very small, but it basically consists of a lot of nodes. So it's very.
Show some of the code, like show the SL diff node, right?
Yes. So this is the SL diff node, which has a specialization for the left long, right long, and will just inject a normal division. And in case it's a big integer, we will just use the big integer version here. The important thing to know is that there is actually something defined that we call implicit cast that automatically can promote a long value to a big integer if just one value happens to be a big integer, because in this case we can just reuse the normal big integer case with the cast to big integer from the long value.
So that shows us how to model an expression node. It's very simple and easy
yes.
to follow, which
yes.
is great. Could
yes.
you also show us how to do a variable set?
Yeah, SL if node, for instance.
So if node will be control flow, right?
Okay.
And this will just have a condition profile that evaluates the condition. The evaluate condition just calls into a child node. And the then part is actually called with execute void. And if the else part is defined, we execute the else part. And it will also cut off the particular branches if they are not used.
As a local variable? Read local variable node.
Yes, so for the local variables, we define specializations where we revert on, this is on frame slot type exception, and we just try to get along from this slot, and if we succeed, we can use this specialization to access the frame. So this is a very simple read. And the frame slot is passed in from the parser, which manages all the frame slots that there are. And these are basically just strings or objects, what do you want it to be. Yeah. Anything more? You want to see more?
That was extremely helpful, thank you.
Nice. So what I want to show here is that the assembly for this example division actually contains a division, if I find it. Yes, there it is. Let's find the upjump. Where is it? BC. This one is it, I guess.
The item. Yes, the item. Right.
Yes. Yes, and this is the full while loop. And here we can see that we got a generic IDIF here that got injected by the compiler. So, anybody has a suggestion what we can do now? What we can optimize? We heard about these identity value profiles. Let's try to cache on the second part of the division, because if the compiler knows that the second part is constant, we can fold it away, right? It's division by 1 is always the identity value. So let's do this. We go into the SimpleLanguage diff node, and we will just add another. Sorry, I'm not native to Mac. Now I got it. So we cache the write value and store it into a long write cached value. And then we guard on guards write equals write cached. And then instead of dividing using the write value, we will divide using the write cached value. No. Yes. No. It's Apple. So, and of course we want to have still our generic division if in case this cache overflows. So we will define here a limit for now a single value, because we just need a single value. It's limit 1. And we just, it's good so I'm slow, you can follow. And for the generic division, we define that it actually contains the division, the cache division version. We need to give it another name. So we don't necessarily need it, but it's nice if the identity cache overflows. We just go to the insert in generic cache, so we don't have too much code. So if we cache on 100,000 on the right side, it's just not worth it to add additional code for this. Yes. Got it. So let's see how this works.
How does it know to call diff cached?
Because it's the first one. The order matters. So it will try the first one first, and it can, if it can use the specialization, it will use it until the limit is reached. And if the limit is reached, it will use this one.
And it knows about names that have cached on the end, that they get an extra argument.
Function is called diff cached. You rename the function.
Yes. Yeah.
What is the limit? Is it the limit of cache?
The limit of number of identity cache entries you get for this particular specialization. So if we now look at the same thing again, and run it again with assembly, we now got down to 1 millisecond because the division is gone. And what will be inserted instead is just a check for the particular value that the right value is actually 1. So we will just look at this in the IGV. Yes, there it is. And Just I need to zoom a bit. Yes. Yes. And here we see that here is a comparison inserted for 1, that the right value is 1, and in case it is, it will transfer to interpreter instead. So let's extend this example a little bit. Yes?
So somehow what your annotation processor does is that it reads this string and tries to...
So this string, the question was, what are the strings? The strings are actually a subset of Java that the annotation processor knows and processes itself and just injects it on the proper places where you need it.
So does it do any sort of type checker?
Nothing. So it's very simple language. It checks a little bit as far as I can see it from the annotation processor side of view. But usually you don't need to do complex expressions in here, because you can, instead of just using directly a simple expression, you can also do function, right? And then you can have a function that returns along do function, takes along again. And this will just be called instead. So you can do arbitrary complex things in there.
But my question is that what if I make a mistake somewhere here? So will the annotation processor catch it, or I gave it...
So if you make a mistake here, like this, it should actually underline. Yes, it says error parsing right cannot be resolved. So this is all checked, yes. Yes, please.
It could be, before we continue, get, for example, get another result from our value, like for divide by 2 or divide by 3, for example.
That's exactly what I want to do. So I've prepared another example. And now this division becomes polymorphic by the iteration. So it will just trigger from 1 to 2, 1 to 2, 1 to 2. And we can do this better job for 1, and we can do a better job for 2. So this is now the place where polymorphic inline cache really pays off. So what we need to do now if we run this now at the moment, sorry. The problem is that we are slow, because we are overflowing the inline cache, and the generic division gets injected again. If you look at the, it's okay, yeah. So what we can do now is we can increase the limit of inline cache to 2. Again, this number depends on how your benchmarks are. So, so if we run this again, we are again fast. And now it's really interesting to see what the GRA compiler actually does in the background. I didn't dump? Oh, I did dump. Ah, that's the previous wrong example, yes. Sorry. Yes. Now we are fast again. And this is dumped. So if we now look at the loop, it has basically 2 if cases here, where it checks for 1 value and for the...
What is the loop limit? We need to consider the begin, right? We need to go down the begin. Yes. No, I don't know.
Ah, yes, exactly, yeah. Transfer to interpreter, yes. And here is the other check. For 1 and for 2. So if we just forward this. Okay, what if we look a little bit later into the GRA phases that GRA does? So it even sees that there is some if switching ongoing in this loop. So it will actually try to unswitch the loop and create 2 different loops for each particular case. So, yes. So I think this concludes my example. Any questions for this one?
I'm still slightly confused by the method names.
Yes.
How does it know to call div or div cached?
It parses it. The annotation process reflects on the class and sees at compile time and sees that this is just a method that is annotated with specialization, and it will call it using the method name that it reflects.
It calls it when what? Execute is invoked?
No, when at compile time, Java C compile time. Annotation processors are tools to run over the code at Java C compile time, so when the Java code is compiled to bytecode.
Where does the interpreter define the meaning of division?
In the specialization.
The where is just defined.
So the generated node from SLP.
Yes.
If I called it something other than div, would it just do the same thing?
Yeah, so the generated.
Yes. So there is a SLDiff node generated by the annotation processor, which basically does all the speculation work. And if we look into this base node, we see the logic how the next specialization is chosen. So it checks for if instance of left, right, and then it will use the diff cached version of the node. It will also check how many nodes were already inserted in the inline cache and will return the value. And for the big integer case, it will check if it's an implicit big integer, which means it's either long or big integer, and we'll use the diff node instead.
Okay, I'm just expecting the top level routine to be something like execute.
Yes, the execute is here. So if you get to the diff cached is the execute, and this one is actually generated. And it expects from the right a long value. This is a typeboxing elimination. It's some implementation detail.
Okay, instead of calling div, I called it Fred. I would get exactly the same result.
Yes, the name doesn't matter.
Okay.
Shall I do the other example?
Yes. But maybe a little shortened.
Okay. So the next example I want to show is based on zero overhead tracing. So for instance, assume we extended again the same benchmark with a simple thing that checks if the iteration is 10, and then we want to enable tracing. And we want to trace our add node every time it is called. So what we can do naively now is we go into the SL add node, and I prepared here the trace function already that checks just is the result divisible by 1,000,000 and then just prints out bingo, right? And so we add here our trace function and we say if SL enable tracing built-in is tracing enabled. That's the flag that I've prepared. It's just a built-in that gets called if tracing is enabled. Yes. Yeah, and then we call trace result. So when we run this now, you see it runs, and then first time we execute it, it runs with 1 millisecond, then tracing gets enabled, so for each add invocation, it adds the check for the bingo, it always adds to the thing. But we also, what we see here is now is the code size exploded. Code size is now 32K for this simple method. What happened here? The problem here is that this trace function, so truffle partial evaluation, expands every path to the every path that is possible. So it will also expand systemout.println completely. And if you want to see how this looks like, just for fun, And now we need to zoom out a little. And we can scroll down. There's a lot going on if you call system out print line. It's a small function, but it's a lot going on. So the first thing you might want to do here is you put a Truffle boundary here. Which basically says to the Truffle compiler, don't try to expand this. This is way too much code. So if we rerun this again, the code size is now in a reasonable amount. But we also see that we now have a call here. So the actual initial code got a little bit slower because we inserted a call. But the other code, as soon as tracing is enabled, got a little bit faster because the code is optimized like Java code. So, any suggestions what we want to do next?
Well, you want to assume with a compilation constant that this is false or something.
Exactly, that's what you can do.
So it's unlike the branch.
Yes, we can insert a branch profile, but we will do this again manually, I guess.
Yes.
With my super slow. And if this tracing flag is false, the compiler directives transfer to interpret and invalidate. We say tracing visited is true. And now what we now should be, we should now be fast as before. We should now we should be faster because we don't have a call anymore in the normal case if tracing is disabled. So let's see if we are. Again, we are down to 1 millisecond from 2 because we don't have a call if tracing is not enabled. We will just check for is tracing enabled, and then we will trace. And if it's enabled, we have the same speed as before with the call. So we now got kind of both of burst route. But it's still not free again.
You want an assumption.
Yes, perfect. We want an assumption. So we need to modify now. As that enable tracing built-in. We want here a private static assumption. And we call it to the Truffle runtime, get create assumption. And if
Final. Static final.
oh yeah, true. And if the assumption is if this tracing is actually enabled, we invalidate our assumption. And we want to, yes, we want to get assumption somehow from here. So we can now make this private final field. Never enabled assumption. I need it. I checked it. And we will look up the assumption in the SL enable tracing built-in get assumption. And then we will just check if never enabled assumption is valid. We do nothing, and else we call into trace result. Of course, no, we also need to check if tracing is still enabled. So if we run this again, we now got up to speed for the normal case, and this is actually as fast as it gets. There is no check anymore for the if tracing is disabled. So we call this zero overhead tracing. Any questions to this? I can also show the IGV to prove that this is actually really. Sorry? Assembly code. Okay. Let's find the loop. Oh, there is something wrong here. No? But can you find it? Oh no, it's cut off. It's cut off. Oh.
Let's try the IGV.
Yes. Yes. Now we have two versions. The first version that we've dumped, because we is with tracing disabled, where we have just a nice loop again that behaves exactly like our simpler example. And for as soon as tracing gets enabled, we get we get a little bit more than expected, but we have here the trace invocation for the tracer. So I guess this is proof that it works. Any questions for this?
Can we ever go back to the check?
Yes, you can. You can just rewrite your node again and retry it if at a later point in time. The difficult part is that you need to find out when you want to try this.
Yes.
Yes. So we have even a primitive for this we call cyclic assumption, but it's dangerous because you might end up with rewrite loops. So. Yes.
So we will suffer from the fixed point problem that was mentioned, because we told that somehow we have to ensure that we reach to a stable state.
Exactly. The fixed point problem is.
If there is a cycle and
That's every guest language developer needs to be aware of this problem and you need to reach a fixed point at some point. Yeah. If there are no further questions, this concludes my part, and I will hand over to Thomas again.
All right. Yes. Yeah. So actually, I mean, the way we kind of de-optimize out of this this machine code, or in this case, out of this loop, is via the save point, which is showed in the first part, right? This is also why you need the save point, because while you're running the loop, if somebody enables tracing, you need a way to exit the loop and go back to the interpreter. All right. Yes. So I just want to show you a little bit more about some of the work, other research work we're doing around this at Oracle Labs, and explain a little bit on this universe. So at Oracle Labs, we have teams on JavaScript, Ruby, and R. Ruby is on GitHub, actually. R is on Bitbucket. So these are two really large-scale, real-world Truffle interpreters that you can take a look at. And we are also doing C, and I'll later talk why we think that's a good idea. So, and the other thing is we have two research projects right now starting. We are very excited about them. First thing is we want to run Java, not just like normally, like Growl compiler would do it, but we want to run Java on top of Truffle, of course. Because there is a lot of these specializations or runtime feedback that we can do better in Truffle, where Java could also profit from them. And so this will be a Java interpreter interpreting Java that's going to be compiled by a Java compiler running on the Java virtual machine. And so you cannot get more Java than that. And so the other thing is we are starting with an LLVM frontend for this, where we interpret LLVM bitcode. Because we started out with C, but now we thought it would be more practical to also have other LLVM languages like C++, Fortran, or Rust that will be able to participate in this ecosystem. And one reason why we want these languages to participate in the ecosystem is that we also have something special for language interoperability, where multiple languages can talk to each other, which I will explain in a minute. Yes, there was in the first round, like after a couple of minutes, already the question of performance graphs, and this is one of the performance graphs we can show. This is our JavaScript implementation measured against V8 on Google's benchmark suite. So this is their benchmarks, not our benchmarks, and this is showing peak performance. Higher is better, and what you can see is that on some benchmarks we're a little bit faster, some we are a little bit slower, and on composite we are at the moment a little bit slower, but that varies. That varies on the workload and configuration. And I mean this JavaScript engine like V8. Yes, question?
Just wanted to ask what V8 is going to depend on.
Pardon?
I just wanted to ask what V8 is going to depend on.
What V8 is?
Yes.
Yes. Okay. So V8 is the JavaScript engine that's running in the Chrome browser, and it's developed by Google, and it's a special purpose JavaScript engine. And it has been leading the performance benchmarks on peak performance for JavaScript for a while. At the moment, also SpiderMonkey or like however Mozilla currently calls the engine is catching up. But V8 is still sort of one of the best JavaScript engines. And the thing is that this is a specialized engine, so it was only written for JavaScript. It can only execute JavaScript, and it has a lot of special purpose optimizations for JavaScript. Whereas the system that is like our Truffle JavaScript interpreter that is measured against that was developed basically by a team of 2 persons over 1.5 years, because they just need the Truffle layer and these utilities that Christian Hummer was presenting, and they do not need all the rest around it, like no garbage collection work, no heavy like lifting of JIT compilation. And this graph is important for us because JavaScript has been optimized a lot as a dynamic language. And this shows that our approach with these nice abstractions on top can give the competitive performance. And there is really nothing that prevents you from getting the same performance as somebody who has a specialized JavaScript engine. So we also, of course, want to be as fast as C. And this is the performance of C running on top of our Truffle interpreters. And peak performance again. So we have a Truffle interpreter that's interpreting C code, and then you compile this Truffle interpreter to machine code, and this is like the dark gray bar is the best GCC. Like it's normalized 100, higher is better. 100 is GCC 00, and the dark gray bar is the best GCC out of all configurations 02, 03, 01, and the red bar is our Truffle interpreter. And again, you can see, sometimes even faster, usually competitive. We can compile away all of the overhead that's associated with this dynamic speculation. And when we then add dynamic speculation, because when it then brings us something, we can have a benefit. Because that's the thing, if you get something that is great in some cases, you kind of need the base case to be not degrading, right? So this is our C performance, and we are now starting with LLVM. Why do we care about C? So the reason why we care so much about C is that a lot of the languages we are building, JavaScript, Ruby, R, and Java, they are all interacting with C. Unfortunately, but that's the case. So all of these languages have something that they call native interop, or like native interface. Unfortunately, not all of the languages have specified the native interfaces. Often it's just, let's include the v8.h header file and like call some functions, right? So, Ruby is a little bit better. Actually, R is also not specified how the native interface is done. But C is interacting with all of these languages, and one of the things we want for these languages is to be able to run them in a sandbox and in a safe sandbox, right? And C is destroying that sandbox if it's just calling out to C, but we want to have C also executed then in this managed environment where we can guarantee safety properties for C. This is very important. PyPy is a very great project. It also does something around partial evaluation in combination with tracing instead of method cheats. And there is a question on Stack Overflow again, which is always interesting. It says, why shouldn't I use PyPy over CPython? Because PyPy is so fast, right? And The answer to that is that PyPy has tenuous support for C extensions. Yeah. So it's kind of like Python runs super fast on PyPy, but C extension is sort of a problem. And in addition to that, C extension sometimes is slow because you need to go into another execution environment. You have a call boundary. Your compiler doesn't see anything because it's just a method call, and so on and so forth. So the first thing we do in Truffle that mitigates that problem a little bit is that in Truffle we do inlining across languages. So here I have a couple of ESTs that represent the execution of functions in the various languages. And here I have a call from one language to another. And for Truffle, this call, Truffle doesn't even know that this is two different languages. And the Truffle inliner will happily inline across these boundaries. So it will happily just create one compilation body with a C function and a JavaScript function at the same time. Yes, but we do not stop there. We created something else, which is when you pass a value from one language to the other language, usually the approach is, well, when you pass it, you convert it. But this conversion is often costly, and yeah, it can be painful. And so what we do is we don't like that idea. But I have here an example. Here's a C program that has defining a struct complex with and allocating those structs here. And then it is calling a JavaScript program over here. And the JavaScript program is then accessing the R and I field of a property, is the JavaScript terminology, of these objects. And what our system is capable of doing is that we are not converting these structs at this call boundary to be JavaScript objects, but we let the C object flow into the JavaScript program. And only at the very latest point, when the JavaScript program really is getting a value out of that object, we then treat the access to this value as a C value access and then convert the result. Because the result is a double value, so it's going to be converted to a double. And in this way, we can mix and match different languages without paying any overhead on the call boundary. So the way this works again is via Truffle rewrites. This is already should be a familiar diagram to you because I showed it in the first session. And here we have an EST again. And the way it works is it's a little bit like small talk. Like when you have an object and you don't know what this object is about, you ask the object questions. You send it messages. And then the first thing you actually ask the object when you don't know it is like, what language are you from? Like what's your passport, right? So so this is the first message. And after that, the object itself carries the logic on how to access it, how to react to a read message. So the object itself carries around the compute, the logic on how to access it. And this is useful for us. Then you get interesting things like language polymorphic inline caches, right? Because if one place in your program where you have multiple languages, then you get a chain again, right? Where objects of multiple languages are accessed. This is useful for multiple languages. It can also be sometimes within one language that you want to have a representation which is not like the native representation for the runtime. Let's say I have a Java array, but I want to directly have a network buffer that looks like a Java array, and that's not a real Java array. And then this is also very useful. So it's not only between two languages, also for one language it can be interesting to have a more flexible representation of an object. Or you could have a Java array, for example, that says, well, I'm at the moment, I'm the numbers from 1 to 100, but you don't need to allocate me. I don't look like a Java array, but I act like one, right? And in particular, in terms of C extensions, we get very good results with that approach. And this is a benchmark we are running with Ruby. There is a blog post about that also on the web from Chris Seaton. And this is a composite speedup of an image processing library in Ruby. And the CRuby version, it's an interpreter only. It's currently it's 1x. It's like the baseline. Higher is better again. And when we execute this Ruby program, pure Ruby program, on JRuby, then we get about an 8x speed up, like composite, over all of the benchmarks involved. The issue is just this Ruby program has been very slow, so people have started to rewrite the inner loops of this Ruby program to C, because that was usually happening, unfortunately. And so then they did this, and so if you rewrite these inner programs to C, then you get an 11x speed up over C Ruby. So this is now C Ruby executing these Ruby programs, but the inner loops it's calling out to C. But then what we can do is we can actually inline these C functions that are called here into our compilation, and then execute the C version and Ruby version with our engine, and we are like another like 3x on top, right? And one reason why this is so good is, on the one hand, you get better results on the call boundary and you call out to C, and on the other hand, you get better results when C tries to kind of get some field out of a Ruby object, right? Because you call to a C function, you pass it the reference to Ruby object, and then C gets this Ruby object out, like a field out of that. And the way C would do that is usually a lot less optimal than what the runtime would do, because all these dynamic inline caches of accessing the properties is just not existent. So this is where our way of doing these multilingual approaches is paying off. Yes?
Why is that C code so much faster than the pure Ruby code, even though you're building the same compiler backend? So is there an algorithmic difference between the C inner loops and the Ruby inner loops?
Between those two?
Yeah, so
yes. So at the moment, our overhead of accessing a Ruby object is not the same as accessing the C object. There's a difference. We are actually working on removing that difference. At the moment, because Ruby is a complex language, it has something like an SC and an EC, which is, I don't know the names, but it's kind of like two classes. Like the class hierarchy is not, usually class hierarchy is one-dimensional. You go super classes, right? But you have like class hierarchy up and class hierarchy on the side. You have like meta class, and I don't know how the other one is called, but there is a nice calculus in the internet. And so Ruby is very, very challenging. And at the moment, we have a little bit higher overhead of accessing Ruby objects. But we are compiling that away, and of course, I agree. Our goal is that this and this should definitely be pretty much the same. Because we want to go to people and say like, well, I mean, there is no reason to rewrite your code that you have written in this nice abstract language like Ruby and go about and rewriting in C. And a similar problem we are facing with R actually, because R code also, I mean, almost all R packages have been rewritten to C. And we can show that this is just not necessary. Okay. Go ahead.
So this is a really nice result, and it works great when you have source code for the C. In practice, people often don't have access to the source code. Can you do something with C binaries as well, perhaps even just by decompiling them to C source?
Yeah, so the question is whether this only works for source code or also for binaries. At the moment, it would only work for source code. And I mean, thankfully, for a lot of these models, Ruby gems and R models, R CRAN models, the source code is available. Doing it for binary would be possible, because I think it should be possible to build also a binary translator on top of this system. But that's kind of a separate PhD thesis, I would say. So if anybody's interested, we would like to do such a project potentially. But for now, we are focusing on something where we at least have LLVM bitcode available, or some intermediate representation that's not x86 machine code.
And this is targeting the JVM. The examples that you give here are targeting LLVM.
Yeah, so at the moment, we are running our system on top of the JVM. We are reusing the JVM's garbage collector and code cache management system, right? But we have a project running that is called Substrate VM, where we have a VM that can do nothing but execute Truffle. Because of course we think in the future you will not need anything more than execute Truffle, right? Because Truffle will execute all of the languages, right? And so we have a system that is kind of specialized. It's like a pre-compiled specialized small VM that will only execute your Truffle programs. And the benefits we get there is actually a lot lower footprint and a lot better startup time. Because in this system, then the Graal compiler and the Truffle interpreters are all pre-compiled.
But the results where you showed a speed up over C, that's using the JVM.
Yes, that's using the JVM, yes.
So
but
that's
the,
doubly impressive.
yeah, I mean, as a disclaimer, these benchmarks that we're using are from the shootout benchmark, right? So they are not, I mean, it's not like heavy object graph traversals. It's more, it's smaller, like usually array-based calculations that you're using there. But in general, yeah, the most important thing for these benchmarks is the way we generate the matching code, right? And the JVM's runtime system is not so much involved.
So when you see benchmarks, when you run your C code, is it safe C? Like it checks the stack to prevent overflow?
Yes. So the numbers I have on this slide, I had on this slide were with the unsafe C. So we use native allocation for C, but we have like similar numbers when you simulate the C on top of JavaScript object model. Yes.
So a version that would check arrays and
yes, it checks arrays, checks objects.
Okay.
Yeah.
That would be very interesting.
Yeah, of course. I mean, the thing is running whether you check an array on the JVM or not is making hardly ever a difference, because you in 99% of your cases, in particular if you count the cases dynamically, you are checking the array inside a loop, and then you can move the array check out of the loop, and the loop will be free of checks.
Well, in C, it's not always the case. For example, string processing.
Yeah, I mean, it's not always the case. There can be the case that you cannot remove a check, and then you have a little bit of overhead. But I mean, for most of the benchmarks, also for most of our Java benchmarks, whether you enable array bounds checks or not doesn't give you any speed difference, because the checks are just hidden from all these optimizations. And the JVM is very good at doing these optimizations and speculations. And in terms of C, I mean, we have some advantages over a traditional C compiler, which is we can determine the inlining at runtime. So we can be more aggressive about inlining if we see a certain code path is hot. More importantly, we can inline across function pointer boundaries. So if you have, I don't know, you have this JNI construct and you have this function pointer table, right, which is dynamically set up, we can inline across those. And I mean, I mean, this is actually a performance problem sometimes, the JNI boundary, for example, between Java and C++. We can just inline through that. And the last thing is we can do some of this dynamic speculation that help. I mean, this diff speculation would also help for a C compiler. The other thing is we have a profiling feedback for loops. So we know how often the loop was executed. So you do not manually have to like pick and poke on the loop unrolling settings or to like get your max performance out of your application. And this is why the numbers we showed you actually are the best out of all optimization configurations of GCC. And in fact, you could only choose one of them, right? But you know, if you're very good, you can configure. I don't know, maybe you can configure per file and so on and so forth. But that requires a lot of manual configuration. Yeah, there's interesting stuff about C. I mean, C has this register keyword and the inlining keyword of C, right? And both of these are hints to the compiler. So people were thinking, well, the compiler is not smart enough. We are smarter than the compiler. We will have a register keyword. We'll have an inline keyword. It turns out that all of the compilers are ignoring that keyword. Because the thing is just on a reasonably complex program, as you cannot make a better decision than the compiler can. In particular because the program changes and then your whole assumptions about the cost models change. Mm-hmm.
Why is there so much difference between your Graal C version and the GCC best C version? Because if you take all your dynamic speculation into account, you should be much better, you know. But did you analyze where the code really differs and where your slowness comes from?
Yes, so the question is, did we analyze why we are slower than GCC on some of these benchmarks? Yes, we did. The one where we are slowest is actually this one here. I don't know what this abbreviation stands for, but you can look it up on the benchmark shootout game. But it is a recursion where we do not do enough recursive inlining, And this Truffle, like Truffle, has a certain overhead on the call boundary that is higher than a C compiler would have. It's something we can get rid of by clever engineering, but it's at the moment too much work for too little gain on most of the things. There is also, I mean, a C compiler has a lot of low-level optimization tricks that are not yet in crawl, but we are catching up. It's something that we just need to focus on more to put some of these lower-level optimization tricks in crawl. Because, I mean, if I'm optimizing Java code, when I can remove an object allocation, I get like a 50x. So I will do all my thinking will be about how I can do the best escape analysis and the best inlining possible. And only then later on will be the questions of, yeah, I can add another 5% here because I can, I don't know, have this, I think you're showing in some of the benchmarks we had add x plus 1, right, in the assembly code, but inc is a little bit shorter and can make a difference of a couple of percentages because you make the code more compact. But some of the smaller scale optimizations is just giving GCC an advantage.
Shouldn't this be taken care of in the JVM, right? Those numeric optimizations?
Yes, and I mean, crawl itself is a normal Java compiler for the JVM. We get actually great results for Scala, which I can show you, demonstrate you if you're interested in. Because Scala has the nice property that it uses a lot of abstractions, a lot of small functions, and a lot of closures, and a lot of object allocations. We love that code. And crawl itself is a normal Java compiler also. It's competitive with current Java compilers like C2. But for Scala code, we're actually better. We will at some point release another binary on the Oracle Technology Network. Then you can test it on your Scala code or your Java program or whatnot. And you now know how to use the IGV. You can use this IGV also for visualizing the functions of your Java or Scala programs and how we compile them. Mm-hmm.
So going back to this Ruby thing.
Yes? Which one?
So maybe I didn't understand. But so what was JRuby again? So JRuby transforms Ruby to C code?
No, JRuby is just the normal Ruby interpreter written in C. It's called JRuby.
Okay.
But this is just a pure Ruby program, right? And this is the Ruby program, but the innermost loops exchanged to be written in C.
So the JRuby is not then the something which compiles Ruby programs to C code?
No, it's just an interpreter for Ruby.
Okay.
But it's basically the standard. It's the reference implementation for Ruby, right? Yeah. It's called MRI, or JRuby.
So then it's not a compiler, it's an interpreter.
Yes, it's just an interpreter. Okay. Yes. And I mean, at the moment, I think if you test the latest version, we might be here already a lot faster. But yeah, you can download and build JRuby from with Truffle support, and Chris Seaton can give you hints there.
Okay, and another question. So regarding the question that Phil asked, so as you have mentioned, you assume that it's a PhD thesis, but I would assume that it should be super hard problem because you want to do some sort of going from very low level, something close to maybe Graal low level IR to something like Graal high level IR. If you want to somehow, whenever you see the object code of C code, to make it like super fast, because you have really assembly code and you want to somehow learn the high level abstraction.
Yes, you want to lift the assembly code to a little bit of a higher level abstraction. I mean, for LLVM, bitcode is also a fairly low level abstraction, right? And so what we added to Truffle recently, I mean, now we only talked about ESG interpreters, but we can support also bytecode interpreters. It's a little bit similar. It's kind of like you have this while loop with this switch, and then we are unrolling the while loop and like making everything constant, and in this way producing code. So we also support the bytecode interpreters. You need a very good recognition of control flow structures. That's hard. And then there's just a lot of work in simulating a fairly complete set of internal instructions, but that's then just a matter of completeness. I think it will be possible. But for now, we have no blinds because in most of our use cases, the source code of the C extension code we want to execute is available.
Just a note to that, basically binary to binary translation. Actually now, given that, for example, NVIDIA is building code morphing CPUs again, I think that might really be something that should happen at some point. Because basically we're emulating x86 assembly or now ARM assembly on hardware.
Right, yeah. Okay, cool. Yes, so I got here an acknowledgement slides of all the people. Yeah, it's a lot of people involved in that project. So, it's a lot of people at Oracle Labs. We have large teams there that work on the various aspects. And we also do a little bit related to query and database processing, because what we do is we try to compile database queries with the Truffle system also to optimize machine code, and then also apply the similar tricks on specialization and creating optimized code. We have a lot of university collaborations. JQ Lynch, University of Edinburgh, University of California, Irvine. They did a Python on top of Truffle. We worked with Purdue University to kickstart the R on top of Truffle, and TU Dortmund also R. University of California, Davis. We work with an R statistician to help us create workloads for R. Actually, this is a major problem that R doesn't have a lot of nice benchmark suites. And we also work with University of Lugano on profiling and related optimizations. Yes, so this is the acknowledgement slides in a text form. This is a little bit smaller group of people, which is the core Truffle and language teams. It's from various different countries. They work also from various different countries. And yeah, so we of course have both internship and full-time positions because yeah, the universe is very rich that we're working in here. And there's a lot of different aspects where some of them can be very interesting, and we always like to sort of increase the number of people working on these various aspects, because I mean, we got like interesting ideas is fine, but you need like also a lot of hard work to get these interesting ideas then adopted and finally used in industry. All right, with that, I conclude just in time. And yes, if you have any more questions, yeah, either now or I can also answer them later during lunch. Thank you.
Again, very well deserved.
Thank you. Thank you.